Welcome everyone to section number 2 here in chapter 4. This is the definite integral, and this is really more of an intro video of kind of where we are going with these things. And the claim is, right, for a while now we've been doing approximations for area under curve, but we haven't really talked at all about accuracy, right? How do we get better approximations? And the claim is we want to get better approximations for this area under the curve. And so how do we do this? The claim is with more rectangles comes more accuracy. So the more rectangles we have in general, the more accuracy we're going to get. But that means that we're going to have to add together, 100 or 1,000 or maybe even 1,000,000 numbers, right? If we're adding together a bunch of areas of rectangles. And so we need to think about a clever way in order to do this. So let me go ahead. I want to justify this statement here that with more rectangles comes more accuracy. And I've made this Desmos applet here. And so I have it all ready for us, but you can click and also bring this up. And so here's what it's looking like. I can go up here and see, here's my function, x squared over 8 plus 1, so just some function here. I have my left endpoint, my a value set at -1, and my b value set at 3, but you can of course wiggle these around, right? So, okay, I'll keep this at -1 though for right now. And let's see, we have this set down here. We actually have a choice of number of intervals, and then we have the c value here is actually for c equals 0 we do a left-hand sum, and for c equals 1 we do a right-hand sum. So you can see that the height of that one rectangle is attributed to that right-hand endpoint. But if I go ahead and I move that to 0, right, c equals 0, this is going to make left-hand, right? So now the height has changed. So you can kind of flip this back and forth, and this will come up here in just a second. But okay, let's go ahead and start off with the right-hand sum. And let's change the number of intervals or the number of rectangles. So if I do maybe 2, 3, 4, right? Hopefully we can see from 1 to 4 that maybe this is getting a little bit better, right? The areas seem to get a little bit better, but if as I do more and more of these things, maybe my maximum here is 100, right? This area now of these 100 rectangles, it looks very, very close to the area under the curve, right? I can zoom in and still see that, yes, they are actually, 100 rectangles here, but they kind of look like they're approximating the area really, really well, right? These kind of like they line up really nice. And so we can see, again, kind of with these fewer rectangles, right, there's more error, right? All of this is too much area, too much area, too much area. But as you get more and more rectangles, right, you have less of that error, right? It looks exactly like the area under this curve. And in fact, you can go up to 100, and you can even add in here, like if I wanted to go to 1,000, right? Now I can't even see those little jagged edges. I guess if I zoom in a bit, I could probably end up seeing these things. Yep, there they are. So now we have 1,000 different rectangles. And then finally, the last thing that I want to do with this is that notice that if I do a left-hand sum, let me go ahead, let me turn this back to 100 here. But if I do a left-hand sum, right, so if I do, boom, left, notice that we get a same story. So it doesn't really matter if we have left-hand sum or right-hand sum. Now we kind of have, there's some underestimates going on. But kind of as you get more and more rectangles, again, it looks like this is the actual area under this curve. So it doesn't really matter the difference between a left-hand sum or a right-hand sum. Kind of both of these will be approximating the same value. So in our course, right, we're going to kind of use this right-hand sum, but you could also use the left-hand sum. All right, so hopefully this has convinced you that we want a lot of rectangles, because if we have a lot of rectangles, we get more accuracy, right? And we approximate the area under this function or this curve a lot better. So let's go ahead, and the claim is there's one more issue that kind of comes up. And so let's go ahead and try this. So suppose I want to approximate the area under f of x equals x. So a very nice, easy function here. It's just a straight line, slopes 1, intercepts 0. And I want to do this on the interval from 1 to 2 using right-hand sums. Like I said, we're going to use right-hand sums and 100 rectangles. So quite a few, right? Not as many as 1,000 or 1,000,000. We'll hopefully get up to that eventually. But I want to do 100 rectangles. Okay, so we're going to do this problem just like we did kind of all the ones in section number 1. Maybe the first thing we're going to figure out is what is our delta x, right? So this is specifying the number of rectangles, 100, n equals 100, and I want delta x here. Well, the claim in this case, well, since our interval maybe is length 1, right, it goes from 1 to 2, so in total we took one step, right, and I have 100 different pieces that I want to break this up into. Kind of the idea is that this is going to be 1/100th, right, so each rectangle is going to have a width of 1/100th. To some extent, you can really do this as 2 minus 1, so that's the width of this thing, divided by 1/100th, and we'll formalize this a little bit later. But again, so the width of each one of these rectangles is going to be 1/100th. Okay, so now if I go ahead and I break up my number line, or kind of if I made a table of values, right, here's 1, here's 2, and so my first rectangle would be from 1 to 1 plus 1/100th, right, 1 plus 1/100th. And then after that, we would have 1 plus 2/100ths. Something like this. I should probably go ahead and start simplifying these. I'm going to say this is 101 over 100. And this is going to be 102 over 100. And then we would add another hundredth, right? 103 over 100. And so on and so forth, right? These are obviously kind of too big. And then finally, I would have like, what, 199 over 100? And then finally, this one would be the same thing as 200 over 100. So notice again, kind of each one of these steps, each one of these delta x's right here is 1/100th. So I keep on taking that same step here because that's the width of each one of my rectangles. Okay, now it's time to get out the function's heights, right? And we're going to be using a right-hand sum in this case. So a right-hand sum, well, all of the widths, right? I'm going to be calculating out area here. So this is the widths. They're all going to be 1/100ths, and then times a bunch of heights, right? Because that's going to give me the area of a rectangle. So notice I chose a very easy function. So actually, the function's value is the x value. So in this case, so okay, if I'm choosing a right-hand sum, right, I have a choice between 1 and 1/100. Sorry, 101/100ths. So in this case, I'm going to choose the right-hand endpoint. So this is going to be 101/100ths. So that's going to be the height of the function on the first rectangle. On the second rectangle, I'm going to choose the right-hand endpoint. So that's going to be 102/100ths, and then 103/100ths. And if we'll keep going for a long time, and then finally we'll have 199/100ths, and then finally on the last rectangle here, we're going to have 200/100ths, or that's the same thing as 2 in this case. All right, and so I do this problem, right, because the most we can simplify this, imagine that we don't get calculators or anything like this on quizzes, exams, shouldn't even use them on the homework necessarily, but if I factor out 100 from each one of these denominators, right, we'll have 101 plus 102 plus 103 plus all the way up to plus 199 plus 200. So I need a way to be able to evaluate adding together lots and lots of numbers. In this case, there are 100 numbers here. To add together. And the question is, well, is there a trick? Is there a fast way to do this, or do we just have to manually, add each one of these together? This would take forever, right? And the claim is, right, there are actually some tricks or some rules, some theorems, better yet, in order to add together many, many numbers. And so that's where we're going with this. In our next section, we're going to be talking about how to add together lots of stuff. And the question is, why are we covering this? It's because, right, we want to be able to add together the areas of lots of rectangles, because that's how we get good accuracy, right? That's how we can really do a good job approximating this area under the curve. All right, so I'll see you next time where we learn how to add together lots and lots of numbers. See you then.